Okay, everyone. So we're going to move on to section 3.5. So these are limits at infinity, and I don't actually like that title for this section. It's really limits as x approaches infinity. But okay, approaches. So infinity, or actually negative infinity, depending on if you're going to the right or to the left. But in any event, limits at infinity, I guess, is okay. Just realize that infinity, of course, is not a number. So, you know, at infinity doesn't, that phrase doesn't even make sense, right? Where's infinity? It doesn't, you know, it's an idea, it's a concept, right? So here's our first example, right? We're going to consider the function f of x equals 4x squared minus 3x plus 5 divided by x squared plus 4. And the question I want to ask is, what happens as x increases, right? As x gets bigger and bigger and bigger. Okay, so let's start with x equals 0. If you plug in 0 into this function, well, you can check that, but let me try it here. So if I plug in 0, I just get 0 minus 0 plus 5. So 0 minus 0 plus 5 divided by 0 squared, which is 0 plus 4. So I really just get 5 over 4. Yeah, that's a 5, not an S. And 5 over 4 is the same as 1.25. So that's where this 1.25 here comes from, right? And so you can plug in other numbers like 10, 100, 1,000, and I'll save you the trouble of doing that. You can obviously just use a calculator to do this. So you plug in the numbers, and the y coordinates are these, right? So I think now we can sort of ask the question, what happens as x gets bigger, right? I mean, of course, bigger is a relative phrase. You know, what's big? 10, 100, 1,000. A million you might think that's bigger. So as x gets bigger, right, and certainly 100's bigger than 10, 1,000's bigger than 100, 10,000's bigger than 1,000, and so on. So the y coordinates are doing this, right? So at 10, y is 3.6. At 100, y is 3.96 or 3.97. And at 1,000, it's 3.997, and so on, right? So you can see that, right, as x gets bigger and bigger, the y values are not getting bigger. Well, I mean, they're getting bigger, but only slightly, right? So if you were to plug in, say, a million, you would probably get 3.999997 or something pretty close to that, right? So 3.99999, that's getting close to the number 4, right? So the way to write this is, right, we write the limit as x increases without bounds. Now that's the proper way to say it, but you can also just say x goes to infinity, or x approaches infinity, right, of the function f of x, and this is in example 1, that's the function. So what happens to f of x? Well, it gets close to the number 4. So this limit would equal 4. Right? And notice that you can go the other way as well. You can go in the negative direction when x is negative 10, negative 100, negative 1,000, right? So going in the opposite direction, in the negative direction, the y values still get close to 4, right? They're slightly bigger than 4, but, right, as x continues to decrease in the negative direction, right? So negative 10,000, negative 1 million, negative 1 billion, and so on, the y values seem to be getting close to 4, right? So we can also say the limit as x goes to negative infinity of the same function is also 4, right? Now, in this example, you can think of that as maybe a coincidence, that whether you're going to positive infinity or negative infinity, you get the same value, you get 4. That may happen, that may not happen in other functions. Okay, so just keep that in mind, that this only applies, that these end up being the same value for this particular example here. Okay, so I hope that at least gives you some intuitive idea of what we mean by a limit as x approaches infinity or negative infinity. Infinity just means you're going to the right forever, and negative infinity means you're going, to the left forever. Okay, so what happens to the y values, right? Okay, so the formal definition, the mathematical definition is here, and you may want to look at it. It's the epsilon. There's no delta here, but there are epsilons, and just briefly, just to explain what this means, right? So the definition as x approaches positive infinity, right, of f of x, that's going to be some number L, if for every epsilon there exists an m positive, some positive n, m, such that this absolute value, the difference between f of x and L, is less than epsilon whenever x is bigger than m. So again, I don't really want to get too deep into this. This is really analysis here. But all it's really saying is, it might be helpful to look at a graph here. And I'm not going to use this particular function, but in general, right, here's the x-axis, here's the y-axis, and then we have some function. Let's say the graph, looks like this. So this is x equals 1, x equals 2, x equals 3, x equals 4. So let's say this is x equals 2 here. And just for reference, this is all y equals 2. Suppose the graph were to look something like this. Be careful not to get too close to this line here. So what we have is a graph where as x gets bigger, the y values get closer and closer to 2, right? So here it might be, 2.1, here it might be 2.01, here it might be even closer, right? So 2.1, let's say 2.05, 2.0001, and you're just getting closer and closer to this horizontal line y equals 2, right? So what that means is the horizontal line y equals 2 is a horizontal asymptote. So in fact, we use, I'm trying to spell it out here, horizontal asymptote. All right. So what that means is as x, so let me write out the limit again here. So we have the limit as x approaches positive infinity of whatever this function is. I'll call it g of x. Right, so this is the graph of some function g of x. That's going to equal 2. It's going to equal to 2, the number 2, right? So again, that doesn't maybe explain this definition here, but here's the idea, right? Suppose we want to be very close to 2, right? We want to be within epsilon of 2. Let's say epsilon is 0.1, right, or 1/10. Okay, so we want to be within 1/10 of 2. So we can be as big as 2.1 or as small as 1.9, right? And you can see that if I pick some x over here, the y value is certainly not going to be between 1.9 and 2.1. It might be 3.5 or 4 or 3.9 or something, but certainly not between 2.1 and 1.9, right? So this statement here is basically saying that our g of x, can I squeeze that in here, right, minus our limit. Now our limit here we said was 2, so L is 2 here, has to be less than 0.1. So this x here would not qualify for that, right? So this is not true for all x, but it has to be true, and this is the important part, whenever x is bigger than some number m. So that m might be very large, right? It might, right? It might not be, this x here. This, I don't know, x might be 5 or 6. It might not even be true for x equals, 7 or 8. But if I said, I need to make that clear here, right? If this is 2.1, then that just barely qualifies. So this might be x equals, let's say x equals 10 or something. So so x might have to be bigger than 10 in order for this statement to be true. So eventually, and that means as x is big enough, bigger than some number m, eventually your y values will all cluster around this limit here, 2, right? And so it has to be close enough to 2. How close? Within epsilon. Okay, so that's the definition. And there's a similar definition for going to, if you notice, the only difference here is you're going to negative infinity. And so here x has to be less than some negative number. So way over here on the left. But it's a very similar definition, right? So if you understand one, you understand the other. And so the point is not to go too deep into this, because I'm not going to ask you questions about, epsilons or deltas. But this is the formal definition of what it means to be a limit as x goes to infinity or negative infinity. For our purposes, I'm more interested if you understand this, that using the table here to calculate values of x when x is getting very big, going to infinity, or when x is very, well, I'll still say big, but big in the negative sense, going to negative infinity, right? So there are two different limits, one going to positive infinity, one going to negative infinity. And the fact that, they're both equal to 4 in the first example is a coincidence. They don't have to be equal here in some cases. Okay, so I mentioned this horizontal asymptote, and you can see that that's essentially the definition of a horizontal asymptote, right? What is a horizontal asymptote? Well, it's a horizontal line, y equals L, right, in such a way that as x either goes to positive infinity or negative infinity, the limit will be L. And that just means that the graph will get closer and closer to the horizontal line. In this case, y equals 2. In the case of example 1, it would be y equals 4. Right, so you just have a different asymptote for different functions, right? So it depends on what your f of x is, right? And of course, some functions don't have horizontal asymptotes. If you just look at the example, say y equals x, that does not have a horizontal asymptote, right? The graph, terrible looking graph, but I'll do the best I can here. It's just going to be this line here, right, going on forever. So as x gets bigger, the y values just get bigger. They don't get close to any one particular number, right? So in this case, you could say the limit as x goes to infinity of y, which is just x here, well, as x goes to infinity, x goes to infinity. So you can say the limit is infinity. But by that, we really mean the limit does not exist, right? Infinity is not a number. It's not like 4 or 2 or 7.8, right? It's not a number. So this is somewhat informal here, but we've already explained that, right, the limit can be infinity or negative infinity. That's just a very specific way of saying that the limit fails to exist. The limit does not exist. Okay? Right, and, to use the same example here, if we take the limit as x goes to negative infinity of x, well, now negative infinity is to the left in this direction. What's happening to the y values? They're not going up, they're going down in the negative direction. So here you would get negative infinity, which is just a more specific way of saying the limit does not exist. It does not approach one particular number. So I hope that helps at least explain the concept of limits approaching infinity or approaching negative infinity. Or as the book would say, limit at infinity, but I already told you that I don't prefer that language, but it's okay if you don't take it too seriously, that there's no at infinity, right? Where is infinity here on the picture? There isn't any, right? You have to just keep going to the left forever and ever, and you're never going to get there, right? So it's an abstract concept, right? Infinity is just the idea that you can keep going, right, to the right forever. And negative infinity is the same idea, but now going to the left forever. Okay? So I hope that helps.